compliqué, ouais.
Okay, hello everybody, and today I'm going to present
Xavier, you need to unmute yourself.
Okay. Well, let's go. The subject is identification from binary measurement. My presentation may be a bit long, but I can cut it where we want. There are several sections independent. First, the context. I want to realize identification. Here I'm only focused on discrete time system here. And the system I want to identify is GEO. The specificity of the problem here is the fact that the real output I can't measure it. I only have a binary measurement of the output. On the output of the system we have a binary sensor which depend on the threshold. If the output of the system is superior to the threshold, I have an answer, SI, and if the output of the sensor is lower than the threshold, I have S low on the binary output. CEO, it's a threshold, a constant threshold. For simplicity, here I will take CO equal to 0, but it's not a problem if it is different from 0. And what I want to do is to identify the system with only available data, the input and the binary output. Why this context? There are several reasons. Maybe the high resolution sensor is too expensive and you don't have enough money. You choose the lower resolution sensor, a binary sensor. Another reason is maybe the high resolution sensor can't give you enough data. Maybe with the high resolution sensor, you have a measure every minute, but you need a measure every second. You choose a binary, maybe to have a measure each second. And another reason is the case when you don't have enough place in memory, for instance. It's easier to store low resolution data. A short example, a few years ago, I worked with a company who developed a small device. You wear it, and this device has to measure accelerometric data, temperature, and the use of this device is there are several uses. To monitor activity of frail persons, circadian rhythm and analysis of the sleep, analysis of sleep quality. And the idea is to store only binary data because we don't have enough place on memory. It's just an example. Among a lot of other examples. The literature on the subject, there are in means approximated 4, 3, 5 papers per year since 15 years. Sometimes the whole paper are not interesting, but some of them are a bit more. Mine, for example. The parametrization. I choose only a simple system. I will focus only on finite impulse response system, but infinite it's possible. Here we have the usual parameterization with theta zero, the parameter of the system, and phi the regression vector. Well, and the objective is to estimate the parameter vector. Just a point, I have made some mistake in the presentation on the indice n. In some page, it will have a small difference, n plus 1, n minus 1. It's not just a presentation error. Well, in the following, I will provide you several techniques, independent. There are other techniques, but just a catalog of solutions. I don't want to compare them. It is just a description of this solution. The first one is a solution based on super vector matching. I choose this first solution because it is very simple to understand the principles. In this solution, the two levels are 1 and -1 on the answer, and as you can see on the figure, we have two populations. On the figure, I draw two populations of phi. On the right, in red, I draw the observation vector, which provides me the answer 1 on the output. And on the other hand, on the left, in blue, the phi regression vector, which provides me an answer, a negative answer. And you can see we have two classes. The boundary between these two classes is parameterized by theta zero, and then finally our identification problem is just a classification problem. And we can see that even if we don't have on this simple example, even if we don't have high resolution data, it may not be a problem to estimate the separation, the parameter vector theta zero. Alors, it is possible that there is some noise on the data. Then it's possible that some regression vectors are on the wrong side of the boundary. So if we have to choose the classification algorithm, it must first it must provide us the boundaries, the parameterization of the boundary, and also it must take into account these outliers. And that's why we have chosen super vector machines solution. This is the principle. We reformulate the identification in a classification problem, and we have just to choose a classification algorithm. The implementation of this solution is very simple. I'm not expert in super vector machines, but I only a user, and I take a MATLAB function in order to apply this solution. Here in step 1, you have the problem is super vector machine, which provides us the parameterization, the parameter vector of the boundary of the separating hyperplane. And once you have computed this parameter vector with the parameter of the boundary, you have to normalize the solution. I don't speak about it before. Often we have to normalize the solution. Often this algorithm are two-step algorithm. In the first time, we compute a parameter vector, and in the second step, we have to normalize it because, as you see on the note in the pages, we have the parameter theta gives the same answer than the gamma theta with gamma positive. We have to normalize the parameter vector estimate with an information of the system, for instance, the static gain, the parameter the first parameter of the impulse response. There is several assumptions on normalization. All of these assumptions are equivalent. Just a short theoretical.
It depends on the threshold then. When you see your pictures.
J'ai laissé le
No, when you see your pictures, the separation of both populations, I imagine it depends on the threshold.
Yes, yeah.
And so you have to. And the threshold is imposed by the sensor.
The threshold is there is several. Sometimes yes, sometimes you can choose it. There is several paper on constant or not. You can choose it or not.
So it's not another parameter.
No. It's if I have a threshold different from 0, I can integrate it in the regression vector, the parameter vector.
So it can be computed automatically. I guess this is the
yes. With theta you can compute the threshold. Just a short theoretical result in order to show that some results have been given. This result depends on some constraining assumption on the input, for instance. But if you, for instance, here, if you have an input, a wide Gaussian noise, for instance, or a wide uniform noise, and if the noise is bounded in white, you can obtain convergence. Here, almost surely toward theta 0. There are some convergence results. A short example on this algorithm. Just a very short example, numerical example. Here I have a continuous time system, and I want to estimate its impulse response. Here I choose a threshold equal to 0, an input which coherent with the theoretical result, the noise also, and I use 2,500 data to obtain this one. In black, maybe you will not see. J'aurais dû mettre plus gros. In black, the real impulse response, and in red, I try 10 realizations of the noise. You can see very a small variant, and a priori the bias is low. There is no bias. Just an illustration. I don't have the time to present you performance in function of the noise, in function of the noise level, or data length. I don't have the time. Just it was just a description of what we can obtain. This is the first. The first solution. Just a few remarks on this first solution. The good point here is the fact that the noise is taken into account. It's not every solution don't have this property. A bad point is that here we have only a solution dedicated to finite impulse response. C'est dommage. Another drawbacks is the fact that it can be we can't apply it in real time. The computational time is too important in my mind. With respect to some other solution, and it is not adapted to time varying system. The second solution, independent from the previous one, is a solution using a specific input. The principle of the solution of this solution here we choose the binary sensor Si equal to 0 and S low equal to 1. And in this solution, we have a periodic, the input is periodic. If the input is periodic, the output too. And we focus here, and the objective here is to estimate the real output on the period. We can do this by saying that the expected value of the binary output can be linked to the real output we want to estimate. On equation 4, on the left, something we can estimate. On the right, yi, something we want to estimate. And if we know the cumulative distribution function, if its inverse exists, and it's known, we can see on 5 that we cannot obtain. If we know the expected value of S, we can obtain the real output.
Mathieu, of course, when you say that the cumulative distribution function is known, you need to know also, well, you can say it's Gaussian, but you need to know the variance of the noise. How can you estimate it? How would you do that?
I will a signal without input. And if no input, no output, and I can estimate the variance of the noise. If I know for instance, in the on this distribution, we will have with the distribution of S, we can estimate the variance
based on S also, because on Y I know how to do it, but with S, because of course you have only S. So
comment je l'ai fait, moi ça fait longtemps que je l'ai pas fait, on va dire.
So, but you could apply the maximum likelihood, of course, on based on the S, and since you know that V is created, well, you know that V is a Gaussian process, then you may find the variance. But yeah, so it's possible. Anyway.
It's possible. I already do this in the past. But it's maybe a drawback of this solution. You have to estimate this. You have maybe you know this distribution. I'm not a fan of this solution. It's one of the problems in this solution. The fact that we have this knowledge required. Well, once you have estimate the real output on each time of the period, it's not difficult to obtain to extract the parameter vector on this page. And you just obtain it if you know the output. M, the matrix M, you know the input, but it's not difficult to obtain theta 0. This is the principle and the implementation, the 3 steps. The first, the empirical estimation of the expected value of S. Then in the second step, we estimate the real output. And finally, we obtain the parameter vector. Not difficult to implement. Just one theoretical result. If you have these assumptions, maybe hard assumption, periodic signal, cumulative distribution function known, its inverse exists and known, you have almost surely convergence. the same short example than previously. The difference is the fact that I use here a periodic excitation. And the second difference is previously I have a signal luminous threshold from not far from 10 dB. Here is minus 10 dB. Because in this solution depends on the noise level. We use the noise in order to extract the real output. If there is not enough noise, you can't estimate the real output.
Please, how do you choose the frequency, the excitation signal? Or you choose only one frequency or several frequencies?
Oh, just the frequency of the just one, and it depends on the number of parameters you want to estimate.
There's no problem of sensitivity. I mean, you can choose all. This is surprising because you can choose either low frequency or high frequency. Is there a frequency, a specific frequency to choose in order to obtain the best results, or it is independent of them?
If you want to estimate 10 parameters, you choose a period of more 10, 11, 12.
But you need to have to excite all the frequency in the because otherwise you're constrained.
For example, you have a time constraint of the first order system, and then other two poles on the second order. I mean, so it's completely independent of the.
Here I just focus on the impulse response. I don't care about pole zero. And you have to if I want to implement variable driven, I have to inverse M.
But you have to excite all the harmonics, the possible harmonics in discrete signal. If you choose a period n, so you can have the frequency is 1/n, so you can have n harmonics, and you have to excite all. Otherwise, your M is not invertible. I've tried it for event at Christmas, but you need to excite all. Otherwise, your condition is not true. So you have to really excite all the frequency in. If you choose a signal of period of a fundamental frequency omega 0, well, you have to excite all the possible harmonics up to pi over Ts, and then otherwise your condition cannot hold, I think.
Yeah, actually, there is an issue related to identifiability.
Yeah, informativity, I would say.
Sorry?
Informativity.
If you wish. And the point is that for third order system, you need to have you need to excite at least two frequencies.
Yeah, but that's in PEM, but I'm not sure it's the. I am, but maybe well, I'm mixing it now with the thesis of Ali, because he used then subspace afterwards, but you may not use subspace. Can I just go back?
Anyway, I guess you need at least to excite two frequencies. So how do you manage to excite only one frequency and get an invertible matrix?
Yeah, but that's the same condition. If M is this one, you need to excite all the harmonics, I think, because I guess that's the same condition in the thesis of Ali.
Multi-sinus excitation, perhaps I wouldn't understand, but with
one sign will not hold.
I don't understand how it works.
Well, then if you have only one sign, this as rank 2, because and so you need that, but you need invertibility, so you need rank n, and so rank n it's not related to theta, because that's sort of because you want to invert that particular matrix.
I just want to invert this matrix.
And you need then to excite all the harmonics. So that's not the same condition as in PEM. So that's in PEM you would have that. So you have 3 parameters. You need at least 2 signs. But here I guess you need to excite all the harmonics in the period. But so if you have period n, then the frequencies you need n frequencies So well, that's possible. So you need the frequency 0 and you need the frequency pi also, and all the harmonics into it. Well, that's what I'm not sure. I've tested on some example, but with one sinus you have only rank 2 then.
I agree. If we choose the wrong input, you can't adjust it. It's finished.
Sorry. Well,
No problem. The short example, just the page, yes, and here result seems I should have chosen another number of data. Here we obtain this result, high variance. If you want to reduce the variance, you have to have more data. I should have. We can see that the bias is seems low, but the variance here is important.
Please, could you explain again this figure? Well, what does I stand for?
I am looking for the impulse response of the system in black.
Response of the system.
Well, I don't. Well, it's in this presentation, I only focus on finite impulse response.
Okay.
So
Yes, I understand. It's
Okay.
not
That's
that.
why
Yes,
it's
same computer.
it's I choose
You rebuilt the impulse
choose,
response from, and
my example is very confusing.
No, but
agree.
No, it's not. It's not.
now it's clear. It's more clear.
I want to estimate the black line, and I realize 10 identification, 10 realization of the.
Mathieu, I have another question. In both methods that you showed us, do you have any hypothesis on the gain of the system?
Always found, not this one, because this hypothesis is compensated by the hypothesis of the noise, but in the previous solution, yes, I have. I don't remember what I what I use. Maybe the norm of the parameter vector, or sometimes it is the first parameter of the impulse response. Sometimes the static gain. Sometimes the norm of the parameter vector. It is just a normalization assumption. Every assumption, normalization assumption, are equivalent from my point of view.
And so here, your result is the mean values of your
well,
time realization.
It's not the mean values. It's all realization.
Okay.
Yeah. At the end, for instance, you have 10
Okay.
points on the right. The variance is emotion.
and can you not regularize? I'm testing all my questions. So can you not regularize? Because of course you have a lot of parameters, so you could use kernel to sort of to.
You can do this better. I just implement the basic solution. I don't try to exotic. Don't try to be subtil. Je sais pas comment on le dit, mais on l'a compris.
Sorry, but I'm not sure. So also, Luigi will only join this afternoon. So if you want to speak French, it's also possible, I guess. Except if Dimitris wants to everything. But no, he has spoken in French. So he's.
Alors, some problem of good news of this solution is that we can extend it to infinite impulse response system. This is not the case of the previous one. We can do this also for real-time identification. It is adapted to time varying system. A good point from my point of view. But you have up constraint on the input and on the knowledge of the noise. Some drawbacks a bit puny.
Why would it be? Sorry.
You mean that you have to know the dynamics of the systems, a priori knowledge in order to design to select the standardizing inputs.
Yes, yes.
Seamless.
At the end of the presentation, I
That's
provide.
Xavier said.
It's what are the problem of the solution you have to. And at the end of the presentation, I have an application, but on this application, I don't have data with a periodic input. This solution.
It's not possible.
I can't apply it.
And adapted to time variant system, what do you mean by that? Because how is it adapted to a time variant system?
But I can't, in the first step, I can estimate with low pass filter the expected value of S.
Yeah.
I can it's low pass filter. I can do this.
So you can do it recursively with forgetting factors.
Ouais,
What
voilà.
you mean? Okay.
Ouais, voilà.
Yeah.
Third solution. Very simple. Very simple also. This solution is based on the correlation analysis, and the good news is in 10. As you can see, if we have some good assumption on the input and on the noise, it appears we can show that the cross correlation between S and the input corresponds to the correlation between the real output and the input, with gamma term, normalization term. Often we estimate some parameter with the correlation function between the output and the input. From this result, we can see that we can apply the same result. In 11, you see how I can express express the cross correlation between S and U in function of the parameter I want to compute. Once you have estimated the correlation between S and U, we can write this equation in 12. On the right, you have the parameter you want to estimate. M depends on the correlation on the input, not difficult to obtain. On the left, the correlation between the binary output and the input. Here again, it's not difficult to compute it. And then finally, we have this implementation scheme. First step, we estimate the correlation. Then I compute with the sum M. I compute an estimate of theta, and final step, the usual normalization step. Not difficult, and the key point in this solution is the fact that the correlation between the binary input and the binary data and the input is linked to the correlation with the real output and the input. A short result here again, similar to a previous one. If the input is a white Gaussian process, and the noise also, we have also the knowledge of the normalization assumption. We have here again almost surely convergence. The same short example, you know it. I choose an input and a noise which are consistent with my assumption previously, and obtain with the same number of data than previously. I obtain this estimates better than previously, in my opinion. It seems that the variance is lower, but it seems that there is a bias. If you have enough data, this bias is converged to zero. It is not a problem. I continue my, oui, yes. Les avantages et inconvénients. Alors, real-time implementation, good news. Adapted to time various system, good news also. We can extend the result to impulse response, infinite impulse response system. That's a good point. The noise is taken into account. Interesting also. But the main drawbacks in my mind is the fact that the input must be Gaussian. And sometimes it is not possible. I continue my catalog with another solution. Maybe I want to.
It should be Gaussian or it should be white?
Hein? J'avais dit Gaussien. J'ai pas dit Gaussien?
Si, tu as dit Gaussian, but my question is, it should be white. It could be white also.
Oh,
It should not be Gaussian.
You must be Gaussian. And,
Why? Why it should be Gaussian?
It is in the initial result. This in here it's
It's only also Gaussian.
it's
Because the correlation you can compute it for any noise.
yeah, for instance, if you use PRBS excitation, you can't satisfy this. With uniform distribution, I'm not sure it's satisfied.
Okay.
It may be a problem on this assumption on the input. So often you have to know something, the period of an assumption of the input. Sometimes you have to pay a price somewhere. Another solution. Here again, the principle. It's very simple in a sense. Here, the two level of the binary is 1 and -1, and you can see that if, for instance, the binary output is 1 with a normalization gamma, you can press the real output to be between 0 and 2. The same is if the binary output is -1. You can use the normalization term, gamma, in order to constrain gamma y between -2 and 0. And finally, in 16, you can see that using this normalization term, we can constrain the real output to be between 2 and -2, and finally, the binary output can be expressed as a function of the real parameter, theta 0, and a bounded noise BT, a bounded noise bounded by 1. The idea is to here to cast the initial problem in an identification problem in bounded noise, and if you use the gamma term, you can constrain the real output, and you can express this. You obtain this new formulation of the problem. So finally, here from this whole formulation, you just have to estimate a parameter vector, assuming that the noise is between is bounded by 1, and then you have to normalize your solution. It's depicted on the figure in red. The real no, not the real, the binary output, and in black I constrain the real output between 2 and -2. finally, the real output with the gamma term is not far from the linear output. The implementation to solve this identification in bounded noise. Here we use an ellipsoidal algorithm that constrains the error between 1 and -1. It looks like je dois dire, least square algorithm, but there is only a variant on the sigma parameter sigma. I don't give the expression of sigma. It's not interesting, but it is used in order to constrain the error between 1 and -1. This is the first step, just a well-known algorithm. And in the second step, finally, you normalize your solution. Yes.
J'ai trompé mon truc.
A result. Less interesting than previous result, but we can, if we have a persistent excitation, I don't see it, say it, but there is no noise in this solution. In the principle of the solution, there is no noise. Then you can have this asymptotical convergence.
J'ai oublié l'exemple numérique, il est par ici, vous n'avez pas verti les pages.
The usual numerical example, like, and what we can obtain with this solution. Not too bad, not better than the previous, but it's a solution among others. The good news, an extension to infinite impulse response, real-time implementation, time-valued system, okay. But the problem is the fact that in the principle, the noise is not taken into account, but consequently, if the noise is too important, it can be a problem on the convergence. I don't have time to present this solution, so I go to a short application, a very short application, just to show that we can. It's possible to apply this solution on real data. A simple system, c'est celui de la thèse d'Ali. The device here is a gas sensor. We have a device that can be modeled by a first order system, and in this system there is a time constant. In this system, there are selective absorbers such that when the concentration of gas increase, the thermal mass of the device increases, and we can show that the thermal mass is depends on the constant. The time constant depends on the thermal mass, and the idea here is to when there is some variation of gas concentration, we analyze. The idea is to analyze the time constant. We have an image, an idea of the concentration of the gas by identifying the time constant. A picture in order to see the size of the device. Not very big, and not we don't have a lot of computational capacity. Storage is limited. Alors, the initial operation mode. to realize the identification. The first time we have tried the identification was not with binary data. And the principle was the following. We have a closed loop. In the closed loop, we use a controller. This controller keeps constant the temperature of the loop. And we use also an external sequence in order to ensure the persistent excitation. And in this initial operation mode, we use an notification algorithm, a closed loop algorithm, in order to obtain the constant, the time constant of the system. This is the initial mode, operation mode. The one variant we have used here is with a binary sensor here. We had a binary sensor in the previous mode. I assume to know the real output. Here, what is the result I will give? It's with this additional assumption. We don't know the real output. I know only the binary output. And the procedure is the following. First, from this binary data, I identify the impulse response of the closed loop. Once I have the impulse response, I simulate it in order to have an idea of the real output. And from the real output, I identify the closed loop. It's a second order closed loop. And from this second order, I can extract. It's not difficult to extract the time constant of the system. The main point is to estimate the impulse response of the closed loop. I don't want to with binary data. I don't want to estimate exactly the transfer function of the closed loop. I don't just in the first step the impulse response a bit like I similarly to the numerical example I gave previously. Experimental condition of the following. The experiment was not far from 2 hours. The sampling period was 5 milliseconds. I cut my data in interval of 2 minutes. On each interval, I estimate my impulse response. And on each 2 minutes, I compute a time constant of the system. And I compare my results with the initial operation mode, in which I use a closed loop identification algorithm. So two solutions in order to estimate my time constant. Output data, the real output, I use the closed loop of Marion algorithm. And my condition with binary data. And I obtain this results. In red, it's what we obtain with high resolution data. Interesting. It's what is depicted here is a relative variation of the time constant. In the beginning, there is no gas. Then after a while, we introduce gas in the device. The time constant, we can observe time constant variation, and we cut the gas, etc. The red, it's with higher resolution, and black, we the results with our procedure with binary data. From my point of view, it is not very bad. I only have binary data on the output. To obtain this result, there is a difference. Yes, the variance is higher, but in my mind, it's convaincant.
Convincing.
Considering the initial lack of information, yes, it is.
Ouais, ouais, ouais.
It's good.
That's bad.
It could be worse. Ouais. Voilà, voilà. Alors, tac, some concluding remarks. I just gave you some solutions, but there are some other solutions. You choose between several solutions. You want to realize real time. Do you have enough computing capacity? Ça dépend de l'environnement. Can you design the input as you want? There is often always a complementary assumption, a normalization assumption. You have to, as I said before, you have to pay a price somewhere. Here I just present results for finite impulse response model, but we can do identification of time series with binary data, possible. Continuous time system identification, possible also. State space model, also possible. And we also have some solution when we only have knowledge of the binary input and output. I only provide you the simplest solutions. There is a lot of other things on the subject. Oh, we are in time.
Yeah, we have even 5 minutes for questions. So thank you, Mathieu. So questions from the room or from Zoom? While people are thinking about the question, I have a philosophical question. You say about this normalization. Is it really always necessary to have that extra knowledge to get good results? Is this sort of arc constraint in your method? If you don't have that, you will never have a good result. Or do you have methods which does not assume, which really use only the data and gets good model?
Well, it's not a problem. For instance, in my example application, I don't have this information. Just normalize it. What I want is to extract the dynamic of the model.
Yeah, but you normalize it. It is the same. So sort of with
I compare in my application. I compare several the behavior several intervals. I normalize in number maybe the norm of the parameter vector. I don't remember how I normalize my solution.
Yeah, but but that's the question. How do you normalize it if you don't know the?
I obtain a solution. I use the this algorithm. Celui-là, c'est lui. Non. I use with the bounding nose. I normalize at the end with the norm. I normalize the norm of my parameter vector with 1.
But because you know that it should be 1.
No, I don't know. I don't care. If my dynamic is it's just the magnitude of the
Rescaling.
Ouais, c'est juste un paramètre d'échelle. Si je reste juste sur un modèle FIR, ça me fait juste changer mon échelle de sortie, mais ma dynamique, et c'est celle qui m'intéresse dans mon application, c'est la dynamique qui m'intéresse.
Okay, but so it's up to a gain. So you will never know it up to a gain.
Ouais.
It's
If you don't have this knowledge,
so it's fundamental. So you will there is no method where you don't.
Yes and no.
Okay.
Here I assume the threshold to be 0. If the threshold is different from 0,
Yeah.
and if you know the threshold, which unit of the sensor, you can normalize with respect this threshold. Si tu connais le seuil, si tu l'as fixé différent de 0, tu l'estimes et après tu normalises par rapport à ce que tu connais sur ce seuil. Tu rajoutes un paramètre en plus dans ton vecteur de paramètres. Puis hop. Donc en gros, tu estimes le seuil, et si tu connais le seuil, si c'est toi qui l'as réglé.
Le seuil, disons qu'on le connaît.
Bon, c'est réglé. Alors, s'il est différent de 0 et que tu le connais, tu augmentes ton vecteur θ là. Mon vecteur θ, je mets dans mon vecteur phi, je mets j'estime un terme constant en fait. C'est juste un terme constant à estimer. Donc j'estime le seuil. En fait, dans mon vecteur θ, j'ai le seuil qui apparaît aussi. Et j'ai plus qu'à le normaliser à mon vecteur de paramètres par rapport à ce seuil que je connais. Quoi.
Donc c'est possible.
C'est vrai que là j'ai supposé que le seuil était nul, donc j'étais coincé, mais après, c'est possible.
Ok.
Par rapport à la variance aussi, ça.
We're still maybe a time for one short question. So if not, let's thank Mathieu once again for his presentation.
Désolé pour les oreilles.
So our next speaker is Kevin Collin from KTH in Sweden. So he will talk to us about adaptive control and identification in adaptive control. Hello, Kevin.
Hello, can you hear me?
Yeah.
Xavier, could you stop recording?
Yeah. I was doing it. Stop.